This is geometry lesson 13.6, sine and cosine ratios. So we just finished 13.5, which looked at the tangent ratio, which was opposite over adjacent. And now we're going to look at the sine and cosine ratios of right triangles. So the big idea says the sine and cosine of an angle are trigonometric ratios that, like the tangent, can be used to determine segment lengths and angle measures in right triangles. So we're going to move quickly through kind of the definitions of it because it works just like tangent. We just need to keep them all straight. So it's still going to be a ratio of the two sides based on an angle. So we have the opposite and adjacent and the hypotenuse, depending which angle we're coming from. So from A all the way across would be the opposite. Okay, and then the one that's next to it would be adjacent. We always refer to C across from 90 as the hypotenuse. And then from angle B, over here, B would be opposite, and then this would be adjacent. So it all depends on which angle we're coming from. So for sine, we're looking at opposite over hypotenuse. And then for cosine, we're looking at adjacent over hypotenuse. So every angle has three different ratios: sine, cosine, tangent, and it's just the three different combinations of sides that we could have. And so the way to keep these all straight, at least the way that I learned it back in the day, was SOHCAHTOA. Now, you're not going to have to memorize these, but we know that sine equals opposite over hypotenuse, and cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. So whenever I'm doing these, I always remember back to this SOHCAHTOA as I try and keep these straight, so you don't have to refer back to your notes so much. Now, TOA is easy to remember, SOHCAHTOA. These two can be a little tricky sometimes at the beginning to keep straight, because when you look at this middle one, SOHCA, you're like, is it OH or AH? Which one is it? But to keep it straight, I always just think of the first part, SOHCAHTOA. That part right there has to be OH, right? It wouldn't be AH. We would never say AH as so. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So let's jump right in. Example number 1, just kind of setting these ratios up. So first of all, this is a 5, 12, 13. If you didn't see that, you could use a squared, b squared, c squared to find it. So now we're going to set up our ratios here. So sine equals opposite over hypotenuse from the angle itself. So here's angle P. Opposite would be 5. And now we're using hypotenuse, which is 13. So the sine ratio of angle P is 5 over 13. Well, what about the cosine ratio of angle P? So cosine, so TOA, adjacent over hypotenuse. So from angle P, the adjacent, remember there's always two adjacent sides, but we're not going to use the hypotenuse as the adjacent. So the adjacent side at angle P is 12. And then the hypotenuse is 13. So the cosine of P is 12 over 13. And then we have the other angle. We never go from the 90. We're just looking at the acute angles of a right triangle. So the sine, again, is opposite over hypotenuse, but now we're coming from angle L. So from L, the opposite is 12, and then the hypotenuse is 13. And then cosine of L, again, cosine is adjacent over hypotenuse. From L has two adjacent sides, but one of them is the hypotenuse, so the adjacent side we're talking about here is the 5, and then the hypotenuse is 13. So you'll notice you have the two acute angles in a right triangle, and you've got your 90. The sine of one of them is going to match the cosine of the other because we're using the same two ratios of sides. So the sine of P is the 5 over 13, and the cosine of L is the 5 over 13. So those are going to be equal. And then the same thing over here. The sine and cosine of these two angles are also going to equal each other. Okay, so let's make this useful now. Example number 2, we've got this picture, 24-foot ladder. I'm going to kind of summarize here. The manufacturer recommends that you never make an angle greater than 75 degrees. That means you're standing it up too straight if you get more than 75 degrees, and it could tip. So that is the largest angle that they recommend that you make when you lean this up against a building. So they want to know what's the maximum safe height that you could reach on the building, which would be X. Um, so we're going to go ahead and have to figure out, do we use sine, cosine, or tangent? So we already know how to set this up in terms of this equals this with tangent, and then you cross multiply or you divide. But now we have to take a look, what angle are we using and what sides do we have? So from the 75, this would be my opposite, this would be my adjacent, and this would be my hypotenuse. So I have opposite and hypotenuse. So I look back to SOHCAHTOA, opposite and hypotenuse would be sine. So I'm going to use the sine here because it's opposite and hypotenuse, and those are the two sides that I want to use compared to the angle that I'm going to use. So I write out my equation. Sine of the angle, which in this case is 75 degrees, equals opposite over hypotenuse, so x over 24. This sets up, just like we looked at in the last section, as multiplication because sine of 75 is diagonal from the 24. So all I have to do is multiply sine of 75 times 24, and I will have x. So I'm just going to punch that in. You've got sine, cosine, tangent all next to each other. So sine of 75 times 24. Make sure you close the parentheses when you're multiplying. And that comes out to about 23 feet. So we're going to round that off, about 23 feet. All right, so it works just like tangent. We are just going to have to figure out, are we using sine, cosine, tangent now as we move forward. But the setup and then the multiplying or dividing is the same. So example number 3, another ladder one. You see a lot of ladder questions. You have a 5-meter ladder and it is 1 foot from the wall. They want to know what's the angle that this is making. So remember, when we want to find the angle, we use those inverse functions, sine to the -1, cosine to the -1. That's how we go backwards from the ratio that we've got. So from that angle, here's opposite, adjacent, and hypotenuse. So I'm working with adjacent and hypotenuse, so I'm working with cosine. All right, and then since I'm trying to find the angle here, cosine of x equals adjacent over hypotenuse, 1 over 5. If I want to solve for x, I need to flip-flop the x and the 1/5. And so when I do that, it becomes cosine to the -1, 1/5. And when you plug that in, we talked about this in the last lesson, you're not going to raise cosine to the negative first. So don't put cosine and then try and raise it to the negative first or something like that. That's going to be something totally different. What we want to use is actually the inverse function. We're going to go backwards. We have the ratio. We're asking the calculator to find the angle based on that ratio. So I'm going to use this inverse function. I would have to hit second and then cosine, and it brings up cosine to the -1. So the inverse function of cosine, and then 1 divided by 5. You don't have to type it in as a fraction. You can just write 1 divided by 5. And then boom, we've got our answer there, about 78.46 degrees. And then, of course, they would tell you how to round, or I would on a test. And if it was nearest 10th, you'd round this up to 78.5. Nearest 100th, 0.46 would be fine. Or if it was to the nearest degree, the 4 would leave this a 78 degrees. Okay, flipping to the back. Let's get this in focus for you here. Oh, that didn't work. That's great. All right, now we are in focus. Okay, so we're going to talk about angles of depression and elevation. So the angle of depression is the angle that that line of sight makes with a horizontal line when looking down at something. So I think this is better just in the picture. You're always going to see this with planes, or if somebody's standing on a cliff and they're looking down, the angle of depression. And the key thing is it's actually this angle in here. So you're always going to see this line drawn down. It's going to form a 90-degree triangle so that we can use our trig functions here. But a lot of people want to put the angle in here. When they give you the angle of depression, it's actually in here. And the angle of elevation, somebody looking up, that angle is in here. And what you want to notice is we've got these two horizontal lines. They would be parallel to each other. That means that these two are alternate interior, so these will always be equal. Okay, so here's what it looks like in a problem. Example number 4. You have the helicopter. It's following this person, blah, blah, blah. It's going to give you a whole situation. They want you to see how far is this person to directly under the ground of the helicopter. So you're looking for X. The angle of depression is 24 degrees. We can bring that inside the triangle 2 different ways. We know the alternate interiors are going to be equal, so you could put the 24 here. You also know that this is 90, so you could do 90 minus 24, and that's 66. All right, and then you could use that angle as well. So we can use either one here. Of course, even if we didn't break it down with the 90, we could do 180 minus this 90 minus this 24 inside the triangle and also find out it's 66. So I'm going to go ahead and use the 24 here, but you could use the 66 and it would get you the same exact answer, but you would have to use a different sine, cosine, tangent ratio depending on which one you choose. So let's work with the 24. So we're looking at 2 different things. We're looking at the opposite from the 24, and we're looking at the adjacent. We're not worried about the hypotenuse out here. So opposite and adjacent, that's the TOA part. This is tangent. So this actually, we're going back to tangent here. So if I was going to write this out and I want to find X, I'm going to say tangent of 24 equals opposite over adjacent, so 1500 over X. So when I put this over 1, this is the situation where I'm not multiplying because my diagonals are not numbers that I can multiply. So we talked about in a proportion, you can flip-flop these. And so we end up with X over 1 over here, which we can just write as X. And then over here, it's 1500 divided by tangent of 24. So when tangent isn't diagonal from the number, we're not multiplying, we're actually dividing. So we're going to go ahead and do 1500 divided by tangent of 24. And we'll round that off. We're going to say approximately 3,369 feet. All right, and last but not least, we want to look at exact values, meaning we're not going to give a decimal. We're going to give maybe a square root or a radical answer or a whole number answer or a decimal that's not a never-ending one. So when the lengths of a triangle are known exactly, as in a right triangle, you can find the exact value for sine and cosine. So based on our 30, 60, 90, we know this is an x, 2x, x radical 3. What's the sine of 60? So sine means opposite over hypotenuse. So from the 60, this is opposite, this is hypotenuse. So that's going to equal x radical 3 over 2x. Simplify, I can knock out x and x. And so I have radical 3 over 2. So let's see how that works. Sine of 60 is this number. Now that's not the exact number. We don't want that number. That should be equal to radical 3 over 2 though, based on the work that we just did. So radical 3 divided by 2, sure enough, is the same answer. So this would be an answer we would round, whereas this is the exact answer of sine of 60. So I can do the same thing with cosine of 60. Cosine now is adjacent over hypotenuse. So this would be the adjacent. So the adjacent is x. The hypotenuse is 2x. X's would cancel out. And I have 1 over 2, which is like 0.5. So the exact value of cosine of 60 is 1/2. And let's test it out real quick. If I do cosine of 60, I get 0.5, which of course then is the exact measurement that we have right here. So when I want to find an exact value, you're going to go ahead and set up the ratio and simplify. We're not going to give the never-ending decimal value.